Thank you all for coming. Welcome to an AIA Maine COTE Committee on the Environment lecture tonight. It's sponsored also by Passive House Maine, who we're pleased to be working with tonight. I would like to thank Passive House Maine, Jeanette, John Charette, and Gunnar Hubbard for helping me prepare for this lecture. We are recording this lecture tonight so that we can spread it around Maine to various AIA members in the far outback and other groups as we can find along the way. Passive House is aggressive. It's aggressive at energy efficiency. Passive solar, it's aggressive at minimizing size and loads. It's aggressive at insulation and window systems. It's aggressive at minimizing air infiltration. It is aggressive at minimizing thermal bridging, energy modeling, and building testing. It's an aggressive program, and it requires an architect like Jesse Thompson and a builder like Jesper Kruse to be on the same Passive House page. Both speakers tonight are certified Passive House consultants. Speaking first, Jesse Thompson, architect, AIA board member, lead AP. He's a partner at Kaplan, Thompson Architects in Portland. His firm concentrates on very energy efficient and well-designed buildings, including net zero homes and net zero modular homes, among other things. Jesse's goal is to be knowledgeable in both the aesthetics and holistic technical understanding of architectural construction. Coming from the other side of the equation, Jesper Kruse is a Dutch native here in Greenwood, Maine, designing and building passive houses now for some time, having done multiple buildings. He has designed many of these with different and varying systems and mostly common sense, and we'll be showing Passive House from a builder's perspective tonight. So please welcome Jesse, and following about 45 minutes or so, yes, we'll be talking about building, and as I understand it, you're going to be taking questions along the way.
Yeah. Jesse Thompson, Kaplan Thompson Architects. This is our very well organized architectural company. I think there's 9 of us now. But so today we were trying to hit a bunch of different levels. And I gave a talk on Passive House like a couple of years ago. Was anyone here there at that time? Remember that? Right. So I was actually worried. It's like, how much of the show is the same? So I had to start moving things apart. And one thing that Jesper and I were talking about was we're going to talk a little bit about what the standard is, some about how to do it, but we decided to talk a little bit about what it did to us. So what going down this journey did to us and kind of how we got there. What was the process, and was it done to me as an architect and him as a builder, and how we came out the other side a little different. So I guess this is the technical definition, which is it is a rigorous voluntary building energy standard focused on the highest energy efficiency and quality of life at low operating cost. And there's some it's a German standard. It is voluntary, even in Germany. I think Belgium is starting to make it mandatory. So it is a parallel thing to LEED. It's not a government program. It's only focused on energy, nominally. So it doesn't try to get toxics into it. You can build a toxic passive house. You can fill it full of formaldehyde. You can do anything you want. It's only energy. And my instinct is that in Germany, you can't build a building with lots of formaldehyde. So you don't bother putting that in your energy standard. Here you get points for not putting it in buildings. There you're just not allowed to. So they have this very narrow focus, and this is only energy. So it doesn't care where your building is. It doesn't care if it's in the country, in a city. It doesn't care how you get to the building. So it's just energy. What I think is interesting is the quality of life part. And there's parts of the standard that, as we've been working on, I feel like there's some very Germanness embedded, and it's the same thing that leads to BMWs and Mercedes. And there's there's high comfort things hidden inside the standard. There's the basic rules, and then there's the rules they don't really tell you. And some of those are, feel like trying to build really well-engineered, high-performing things, like a Mercedes. So that's sort of embedded in it. And rigorous is also embedded in the Germanness of it all. I am a certified consultant. I was the last wave of consultants to get certified before the United States Institute and the German Institute had a really messy divorce. So I took the European test and passed it, and afterwards they stopped talking, and now they're starting to talk again. And now there's a German institute and an American institute. They aren't really different yet, but they're just mad at each other right now. That was 2011. If you're, we're at the AIA COTE, so these are the kind of things that atmospheric carbon dioxide levels. We've been at lectures like this. We have the 2030 standard. This is part of the COTE piece of it. And so most of us in this room have been been in rooms talking about energy for a while. This is taken from Martin Holliday, who's a writer at Green Building Advisor, and he went back and did this really great history of super insulation in the United States and Canada. And I grabbed these because they're kind of fascinating. And in 1976, Wayne Schick in Urbana, Illinois, made a super insulated house. And this is about the first super insulated house people can find. And it had double 2x4 walls. It had R30 walls. It had triple glazed windows. It had an air-to-air heat exchanger. This is 1976. We're almost 40 years ago. And the Canadians did their own, and they also got an architect. So, actually, unlike Wayne, I think they got an architect. So they got a really fancy-looking one. But, R40 walls, R60, triple glazed windows, heat recovery, heat exchangers. It has a very good air tightness level, 0.8 ACH 50. Really aggressive. 1977. And Martin has this great show where, this is what was going on at the time. Oil crisis, Carter putting solar panels. His speech is what happened. 1985, everything is ready. All the research has essentially been done, and his answer is, this happened. The Reagan years happened, oil plummeted in price, the energy efficiency thing completely faded. So, 1982, 1985 was when this all came down. His other great reason is that the people doing all the research were hippies and Canadians, so it was really easy to write them off. And that's Martin Holliday in Sheffield, Vermont. Yeah, this is me in 1985. And I grew up 5 miles down the road from Martin Holliday. So I was in elementary school then. But there was a technology jump where the Germans, and they sort of fully admit it, was the research started in the United States. The low energy building movement all happened over here. It was MIT, it was Illinois, it was California, it was all the sort of hippie building geeks working, and Canadians working on it. But when it died here, and I actually saw someone at a conference said, yeah, I ran out of work and I had to go over to Germany to get work from the DOA. And he jumped to Germany because in Germany they started caring about it. So in 1990, he started work on a prototype, and they were talking to people in Sweden. And Wolfgang Feist, who is the Passivhaus Institute, they picked up this North American torch. And here's the first passive house. And there it is. It's a wedge facing south. It looks like the old MIT houses. But being German, this is a townhouse. So these are actually it's a 4-unit building. Because they don't build a lot of single-family houses. It's got sun shading. It's got solar panels. It's boxy. The first passive house in the United States is by a German expatriate named Katrine Klingenberg, and she built a single-family house in Urbana, Illinois. She just happened to be in the same town as Wayne Schick was, for whatever reason. And it's a little wedge, it's a little box. These things travel in patterns. And so I'd like to do a little bit of the history, which is where did all this come from. The Germans were watching people like the Rocky Mountain Institute. There was something called the Factor 10. What they were searching for was, how do we get to energy sustainability? How do we get to energy equity across the entire globe? So how do you have fairness? And what they decided is that they developed something called the 2,000 watt society, which was everybody gets 2,000 watts, continuous. That's your budget. You get like 500 fossil fuel and 1,500, and that's what you get to live on. And they ran the numbers, and here's what people were doing. Here's what they needed to drop it down to. So they need to reduce their consumption so that everybody on the planet could have an equal share. And it was this concept of like, what's the energy going on over your head that's invisible? What's your plane flights to the Caribbean? What's your SUV? What's the energy in your food that comes to you? What's your burden? And, so here's the thing we all know, sort of, is that USA and Canada are off the charts up here at 10,000. We're using 10,000 watts continuous. That's sort of our average if these people ran the numbers. Mexico uses 2,000 watts continuous. So if we live like a Mexican in 2003, that's supposedly sustainable. Bangladesh gets a lot more energy. They get 10 times as much energy to work with. They actually make out really well. And so that's this equity idea. They were trying to figure out what does 2,000 watts look like. This is directly cribbed from John Straddle, Building Scientist. We sort of know what sustainability could look like. This is a net zero life. This is just one little solar panel outside a yurt. And here's the Maine version. It's our grandparents. Like, there's maybe a little propane bottle out back. There's maybe a little electricity. This was a really low energy life we lived in the 30s and 40s. And this is what we actually do. So the gap between this and this is pretty big. We know, and the gap between this and this is really big. So the Germans went looking for how do we, there was this vision also in the 70s that this was the future of what eco-building was going to look like. We would all have greenhouses and solar wedges and waste and mulch and all of these things, which also doesn't really line up with this. And so this is an Austrian passive house skyscraper. This is built to the passive house standard. And it's it's being completed right now. It has photovoltaics embedded in the curtain wall. This is where the Germans went to, was how do we keep modern civilization, the civilization we all seem to like, and not just try and turn the clock back. This is a passive house in France. This is gorgeous high design work. This is one in Portland, Oregon that just finished up last year. So this is not hair shirt living. This is not sell our possessions and go back to the yurt. That was the German concept. So how do you do that? How do you get down to that level? How do you get this kind of energy consumption where this is Energy Star, a LEED certified home, and this is a passive house? It's way down at the bottom. So this is kind of the history, is that when we started trying to be green, whatever that meant, we ended up with some really expensive projects. And we started adding things on to our project. We started piling it on. Got better insulation. We did better windows. We did better this and better that. And our project just kept getting more and more expensive. We ended up with some failed projects because we had all these sort of dreams where we kept piling on the features. And the Germans sort of got that. So they always show this slide, which is, how do you not increase the price of a better project? And what they went to was, you have to get rid of something. And what they targeted was a conventional heating and cooling system. They said if you get rid of your heating system, you can pay for all the goodies. You can pay for all your insulation, you can pay for all your windows. You just have to get rid of the normal heating system that's in a house. And what they engineered was, they said, okay, it's a high quality house, it needs fresh air, it's got a fresh air ventilation box in it. You're buying that. You're not buying a ventilation box. So how much heat does this little tiny tube of air move? And they ran the math. So if you've got this much air going into a bedroom, how much heat can you put in that air before the air starts to smell weird and you start burning all the dust in it? And what they ran that to when they did the math was that added up to 1 watt per square foot peak load. So if you have a 2,000 square foot house, on the worst night of the year, cold wind blowing, 2,000 watts will keep it at 72. And that amount of air can be moved in 15 CFM per bedroom. And you can move that. So this was their big realization. So, a 100 square foot room needs a 100 watt light bulb burning. That's the kind of measure of it. So a bedroom, you need 1.5 light bulbs. Or, a sleeping person would probably get rid of most of that. And this is on the worst day of the year. So these are tiny, tiny amounts of energy. So the German realization was if you can put a little bit of heat in the fresh air that's already going into the room, you don't need anything else. You have no boiler, you have no hydronics, you have no radiant, you have no anything. You get rid of, in most custom homes, we tend to think of there's $30,000 to $40,000 of, nice, these are good custom homes, $30,000 of gear. If you can get rid of that, you could buy a lot of insulation. That's the plan. The plan, how the plan works is sometimes it works, sometimes it doesn't. But so this is embedded in the Passive House standard, which is 1 watt per square foot, which works out to 10 watts per square meter. It's the only math that works easy. And you can certify a passive house if you prove that you can heat it with 1 watt per square foot. The problem is the German climate's a lot milder than Maine, and it's really, really hard to do it this way. So then the real numbers that everyone talks about are the heating limit, which is that you cannot consume more than 4.75 kBTU per square foot per year. This is the certification number, 15 kilowatt hours per meter squared. This is how much heat energy you use. This is the limit. And so I've been working with this number a long time, and it really means almost nothing. This is half of a cup of oil per square foot per year. That's how much you get to burn. 4 ounces of oil. A 2,000 square foot house, this is 60 gallons of oil to heat the entire heating season. It's not nothing, but it's not very much. But they knew that if you only put a limit on the heating energy, people would find ways around it, and heat isn't everything. So they also put a limit on the total energy a house uses. This is your Xbox, your PlayStation, your lights, your everything. And they put a cap, that's 120. That adds up to 38 per square foot. And here's the hard part, which is this is measured at the power plant. So if you use electric heat, 2/3 of the electricity is wasted before it gets to your house. The power plant's running and no one's using electricity. They have to keep it running even though there's no demand. There's these huge line losses and these huge losses on the equipment. So we only get 1/3 of the electricity we make. Where natural gas, most of it gets to your house. It doesn't actually leave on the way. So they have different numbers, which means that if you use an electricity in your house, you only get 40. Because you have to multiply it by 3. So it gets really hard all of a sudden. This is, because what they were trying to do is they were trying to make a factor for burning coal in a power plant versus renewables, versus biomass, versus gas. So if you burn wood, you can use a lot more energy because it does less damage. The damage factor on the total damage. This is about the equivalent of 500 gallons of oil per house, a 2,000 square foot house. This is how much you get, which is, that's actually a fair amount. This is not as strict as the heating standard. This is a slide that I put in because after we've been working for a while, we realized that what was really interesting about Passive House was you weren't trying to be a little bit better than anything. You weren't trying to hit a moving target. It was 4.75, yes or no. Did you hit it or not? And especially in the commercial sector as architects, you work in this weird, 30% better than ASHRAE 2006. And then it's ASHRAE 2009 and you're 40% better. And no one can compare the numbers to the numbers in the back, and they don't mean very much. They're just sort of this, it's this weird fog you're pushing against, that you're 30% better than something that happened in the past. The German standard is very clear. It is 120, it is 4.75, you hit it or you don't. And that's really kind of enlightening. You have a goal to push towards. And that is very clarifying. It leads to a lot less greenwashing. You either made it or you don't. The last one is also fairly famous by now, which is they set a building quality standard for the construction shell. They said how good the skin of your building had to be. And that is measured in air changes per hour, 0.6 air changes per hour at 50 pascals with the blower door running. For those of you who work in the commercial or multifamily sector, this is probably like 0.05 CFM 50 per square foot of shell. It's 5 times more stringent than the MISHA shell standard for buildings. It's 5 times better. This is very tight, and the Germans say this is not only about energy, it's about construction quality. So if you build a very low energy building and there's a lot of air leaking through the walls, a lot of moisture leaks through the walls, and you can rot out a wood building. So if you close all the gaps, you're guaranteed to not have rot from moisture moving through your low energy walls. So there's things embedded in it. This is one of those things where you crawl around with a smoke pencil and a blower door, and you test your buildings, and you You test them a lot when you first start doing them, and you test them less after a little while. Right?
Yeah.
Yeah. And so your first buildings, it's really smart to make very simple shapes. Don't have a lot of corners. They're much harder to do. You know, build little boxes. That's why boxes. You know, it's good to start with boxes. This is one of ours. We got to that level on that pretty house in Falmouth. Actually, right over there. One of this. So we talked about there's a heating energy limit, but that's not all the energy you get. The Germans talk about keeping your building in balance, where 1/3 of your energy is probably coming from stuff in the building, like refrigerators and people walking around. So internal gains are 1/3. And probably 1/3 of it is from passive solar. And passive solar is really tied into Passive House in ways that we're going to talk about a little bit, especially in Maine. And then 1/3 of it is the 4.75 that you're running through a machine. And it can be any machine. They don't care what machine it is. It can be electric baseboard. It can be a boiler. You know, they're not going to tell you what to do that. But you know, you could use a Hello Kitty hairdryer. That would heat a 1,500 square foot apartment for a Passive House on the worst day of the year. And you know, this is for like a bigger window too. So it's tiny, tiny amounts of energy. You know, and there's people in Maine doing this, 3 sticks of electric baseboard, $50 each, is enough to heat a whole house. So $150, you've got enough mechanical system to heat a Passive House. And that's the German cost barrier game. You can heat a house with Home Depot electric baseboard. You've gotten rid of a $30,000 piece of machinery in a custom home. Okay, how do you do it? They give you this insane Excel spreadsheet that has 30 tabs, 40 tabs. It's all in Excel. You can click on any cell and you can see the formula. It's unlike any energy modeling software I've ever seen where it's not a black box and you can go tinker around and you can go look at how they did their math. And you move between all these things. You put in your areas and you go through it. It's very German. There's no graphs. There's one graph, actually. You put in your R values. You know, you build up your assemblies. You type in hardwood flooring, plywood, sleepers, concrete, EPS, insulation, you know, thickness. It calculates the true R value. You have framing factors, 15%. So you comes kind of raw. You have to build it, but you build all your little assemblies in it. There are some oddball things like the groundwater flow rate, depths of the groundwater flowing under your building, because you know cold water going underneath a building slab would carry away heat. No, I don't know. You're not allowed to touch that.
No.
But you have like the R value of the soil. If you're building on sand versus rock, you know, someone might tinker with that. This is people who love like 5 decimal point places, so there's a lot in there. This is the one graph. There's one graph in the entire spreadsheet. There's so few graphs that we had to make our own dashboard, and we made this thing in Excel that has graphs that sits in front, so we can, like, as architects, actually use it. And so we made ourselves pretty graphs that show us where the heat gains are going, where the heat's being lost. And we had to do this just because like it was too numbersy. This is our dashboard that we can like give clients. So basics of Passive House. You're going to be doing thicker walls in the building. You know, people sort of know this by now. Walls are thicker. We haven't changed much. I did this for an AIA COTE lecture and I only kept us a couple slides, but like 1830s, we added 2 inches in 1970s. In commercial, we actually kind of went back and put steel studs and like, you know, an R7 wall is your basic code commercial wall. Here's your architect dream wall. R4, that's what we're all trying for. So there's all these ways, and I think, you know, we used to talk more about this, but I think it's the point where if you want to know low energy walls, we can all probably Google them pretty quickly. If we need to know R40 walls, we can look them up. But I put this slide in, which was, you know, honestly, as an architect, one of the biggest changes to how we did houses was we started drawing fat walls on the outside. I told everybody in the office, like, only draw a wall a foot thick. Just, you know, every outside wall is at least a foot thick. You know, if you're a commercial architect and you do masonry, you're sort of used to that. But like, you don't draw those little skinny ones. You draw the outside's fat and the inside's skinny. And it just kind of normalized it. And that was actually the biggest hurdle because we were drawing our walls too thin. And when we wanted to do this better wall, we had to change all our drawings. And then someone would notice it. And they'd like, well, why did the walls get fatter? Are you spending more money? You know, but when we left it in the beginning, we didn't have to redo all the floor areas. It was just hilarious. Like, so, you know, this is now our rule. Like, always draw about 12-inch wall on the outside. You can always make it thinner, and no one will notice. They're famous for very good windows. This is a Zola window. These are these German tilt turns, which we're now able to buy, that have big, thick, clunky frames. You know, these big insulated frames with foam tucked inside the frame. Triple pane glass. These are R10 windows. American window labels. This is the NFRC label. As you know, as designers and builders, we're used to seeing this, like 0.3. That's what the window is, and that's based on the standard American casement. The German label is different, and this was a big eye opener. They have a sticker that tells you what the U value of the frame is, and then they tell you the U value of the glass, and then they ask for the U value of the spacer, and then they ask for the U value of the other spacer. No, that's the spacer. That's the. So they have a U value for this, and they have a U value for this, and they have a U value for this, and they have a U value for how it's installed in the wall. And they do that so that in your software, you can put any window in and it will tell you the R value. Because windows act differently. So these German windows have kind of equal glass to frame. R9 in the middle of the glass, but the glass is now better than the frame. And this is a good frame. So here's a drawing which Marvin has actually fixed, but the NFRC label hides all this because you have a 0.3 window or a 0.28 or a 0.29, and you don't know how it's getting there. So a Marvin frame is an R2 frame, and their double glaze might be R3.8. So you put triple glazed glass, you've still got an R2 frame. It doesn't get very much better, and that's because Marvin took their cladding, and when they were worried about their sills rotting out, after they rotted out all those sills in the 80s, they ran their aluminum all the way back to the inside of the window. So if water leaks into the sash, it doesn't rot the sill out. So it's it's tough. It means that there's aluminum bypassing the sash. And so there's cold whipping in past this beautiful insulated thing, and it's now R2. They can hide that because no one looks on a chart and says, what's your frame R value? You never look. You just look at the window. The Germans are, oh, look, it's a 0.77. Oh, well, that's better than a 0.8. I'll buy that one. So they've got this layer that's shown us. And when you put in the spreadsheet, it calculates every window in your project. So the first couple times you do it, you start noticing there's different numbers. Like, why is one window a 5.6 and one an 8? They all have the same glass. They all have the same frame. That, we're in Maine. We draw these little windows, right? SDLs. This is mostly glass and this is mostly frame. So if your frame is R2 and your glass is R6, and your glass is R6 and your frame is R2, this has a lot less frame to glass ratio. This is way better insulating than that window. Now, of course, it removed wall, and wall is usually better, but this is a 40% better window than that, and nothing changed about the frame or the glass. That's under the designer's control. So, giant plate glass windows turn out to work pretty well in terms of windows. A few big windows is way better than a whole lot of little ones. And that was invisible to me. So, my daughter asked me to put this in. And one of the other things that's embedded, and you go back to the Germans, this is why I put that in because they have a comfort standard, which they say the surface of the window shall never drop below 68 degrees on the coldest day of the year. And that is so you can sit next to the window with no sweater on and no heating system running and not be cold. So they're checking thermal comfort, which is that you can then sit next to the glass because it's such good glass. And then you don't need heating systems out there. You don't need to put baseboard under the windows. So that it's all this cycle that they've got embedded in here about very high quality products means that you don't need big heating systems because you're warmer. So that's what that is. You're also required to do a thermal bridge free building. And they check for thermal bridges when they certify. And they have a number, and it's a flow number. It's watts per meters per meter Kelvin. It's like a linear coefficient. And this was also, if anyone saw that AIA skins thing, what I started realizing is like in our office, we always talk about these R values. We talk about them a lot, and we obsess over like these R4s and 5s, and they're all not that different. You know, it's like R3, R4, R5. These are insulations. And you know, we talk about insulation all the time. And there's this whole rack of insulations we don't talk about, which is like, you know, softwood, concrete. So concrete's R.7. Glass, in the same category. Stainless steel. We start getting decimal point differences. You know, those other ones were 3s, 4s, and 5s, and these are 3 decimal places. I really did not pay attention to what metals were. I probably learned it in school. Aluminum is not a little bit worse than carbon steel. It's like it's a factor of 300% worse. It's in stainless, like, you know, these numbers really rack up in amazing ways. And, you know, here's the storefront I used to draw. Your basic commercial storefront. The wrap would tell you it's thermally broken. And there's a piece of nylon this big between an extruded piece of aluminum. And we didn't even used to have that thermal break. We used to have solid aluminum, and we can still find houses. And, you know, solid aluminum is, all these do this again, but 0.0009. It's so small I can't even, you know, figure it out. But what's sort of interesting about thermal bridging and why they're so detailed, and I think the commercial sector is really getting it to it, is here's a like R75 wall, and then here's one little piece of steel through the middle of it. It drops the overall value of the wall to R7.5. The flows are so intense through the steel. One little piece of steel going through that, all that money just went out the window. This is dangerous territory. Anyone from Canal 5 here? No. So there's a really nice building, the Hyatt going up in Portland. And you know, this is unfortunately, you built it across from our offices, and we look out the window and get to watch it get built. And so I'm sitting there ranting about something, looking out the window. And I was like, look at those steel tabs. Look at this canopy. They're welded right onto the steel frame. And they've got 2 inches of exterior polyiso on the outside of the building. Like, it goes right through it. That's got to be terrible. And someone in the office is like, how bad could it be? Like, I'm going to figure it out, because I can now figure it out. And, you know, it's actually a really good building. But this is what Passivhaus does. It's 3 square inches of steel going through. It has a U value of 2 inches of carbon steel is a U value of 166. We're used to windows like 0.3. Well, it's 166, the inverse. So one tab has a UA, U times area, of 500. The U value of 2 inches of polyiso, which is on the building also, is 0.83. So that every steel tab is the equivalent of 6,000 square inches of 2-inch polyiso. It's 42 square feet. So every single steel tab wiped out 42 square feet of insulation on this building. There's not that many square feet left. And this runs all the way along. And this is a normal structural detail. Like, you've got to keep the things from falling off the building. I think it's worse. I think it's even worse because this is an aluminum sunshade. And that to me looks like a radiator fit. So when the wind's blowing down the street over aluminum, it's got to be doing an aggressive cooling effort, and that's got to be wicking through those steel tabs probably at a higher point. And I'd be shocked if there isn't ice on the inside of that building on a really cold day in Maine. So, you know, I love the Canal 5 guys, but you know, he built across from our building, and you know, I was just staring at it. So this stuff is kind of amazing. So this stuff is banned. You are not allowed to connect steel to the inside and the outside of a building. This is, you know, I show this slide a lot, but you know, this is not normal architect stuff to do this, or didn't, but it sort of might have to be. But it wasn't that hard of math. It just take a little while. It'll be easier the second time. So this is what Passivhaus did to me. This is what we were trying to do. So when Wolfgang Feist was building his, that's me at the University of Oregon in 1992, back of the truck. I ended up in Oregon, which was sort of an eco school, right, Gunnar? Gunnar was there at the same time.
Yeah.
He was a little older than me. A little cleaner cut, too. I built this house in 1992. It has like a bunch of fiberglass that's falling out of the bottom. This one taught me that mice really like living in fiberglass, and you probably should not insulate a camp at all because, then the mice don't want to live there. The insulation's holding it better since I built it than the tamarack posts we drove into the ground. These are solid tamarack, and those haven't rotted in 20 years. It's kind of amazing. Like, some old timer taught me that. I worked in Boston at CBT, and we worked at, we did the Prudential Winter Garden. So this is like second job out of college. And I had to do a presentation to Casco Bay High School, and I was sort of showing like what I did. I actually dug up this old stuff. So here's a rendering I did in 98. And here's a detail I drew in 1998. And I look back at this, and I'm like, what was I doing? Like, there's no sense that there's an air barrier to this building. I have no idea what's stopping air from blowing through the middle of this. There's like these little kind of insulation lines that are just sort of, and I think I just filled the cracks nicely. It was like, it looked good to draw them like that. I had no sense of what I remember that, just having no clue. And I don't remember anyone in the office either saying like, where's our air barrier? The air barrier code hadn't hit Massachusetts. So it's really, it's funny to look back on what you did in the past. I moved to Portland and started working for Scott Simons. And this is a gorgeous house in Higgins Beach. And, still I remember being really clueless. John Rousseau built this, and I didn't draw a hole for the chimney in the house. So there's no, there was no place for the chimney to go through. And I remember showing him on site, like, oh, wow, there it is. He's like, yeah, I fixed that for you. You could have ruined us on it. But in 2000, I also don't remember talking a lot about insulation. We did poly and fiberglass in 2x roofs. And I know that these buildings, there's a whole generation of them across southern Maine that are having a lot of problems. That the moisture's going through the poly, it's wicking onto the sheathing's rotting out. There's this whole generation of them, the buildings that I worked on and other people did. My partner Phil was doing this out in Great Diamond with Rob. Air barrier, that was kind of a camp, right? Actually had continuous insulation, didn't it, Rob? I had like rigid all the way over the outside, but like rolling doors with no seals. It was, but what shifted things was we started going to the Building Energy Conference in Boston, and in 2006, the Katrine Klingenberg from Urbana, Illinois, brought the German Passive House Institute, and I sat in the room and I watched these slideshows on these buildings, and I remember my jaw just being on the floor seeing this. This is the house she built. She framed it with I-joists as studs, because she dug up an old Weyerhaeuser technical bulletin from Weyerhaeuser, Germany, where they were like, it was a fully approved protocol. So it was like I-joist studs with fiberboard siding to be vapor open to let the moisture out so it wouldn't get trapped by the plywood. It's sitting on 12 inches of foam. I remember just like, what the hell is that? Like, that's the weirdest thing I've ever seen. It makes no sense. Why would you ever do walls that thick out of I-joists? And it, sort of like crazy genius. And I dug up emails recently, and then there's like these emails I was saying like, has anyone heard of this spreadsheet called the PHPP? What is this thing? I was like trying to figure this out from seeing it at the conference. The building, the Bright Built Barn we did, we ran through PHPP in 2009 after it was done. And we hired a consultant to find out how we did. And it's a net zero building. It's like fully like above net zero. The German limit on heating is 15, and this building was a 78. And this is a net zero building. It actually, it's 100, the limit's 120 and we were 148. We're like, oh, almost did that well. We were kind of blown away, and what the Germans were looking at this building and they saw was that we bought our way out of the problem. Is that we did a low energy building by spending too much money on solar panels. We weren't conservative enough. We were using too much energy and making too much energy. And there's an argument to be made that that's okay. But to the Germans, this is like way, way more than a passive house. And then the hilarious thing was we knew about the 0.6 HCA50. We hit 0.6 HCA50. And then we ran it through the spreadsheet. And the guy said, no, you got 0.8. Like, no, we got 0.6. Diane Milliken got 0.6. He's like, well, the Americans measured at the outside of the walls. The Germans measured at the inside of the walls. The difference in volume on a little tiny building, because it's air changes per hour of the volume. This building is so tiny that we missed the limit by 0.2 because the way you calculate, because the Germans think of it like you fill the building up with water, you pour out the water, and you measure how much water. That's how much air there is in the building. You don't count the solid stuff. Americans do it on the outside because it's way easier to do the math. And so we missed the test by 0.2, we found out. And then our consultant, this is the window wake up where he told us, like, your side lights are killing you. Like, what do you mean your side lights are killing you? They're all frame. A tall, skinny side light. It's like, it's all frame. You're better off doing a 4-foot wide door that's all glass than doing a side light next to a door. And in a normal house, this wouldn't matter, but we were doing this tiny micro house and every little tiny thing mattered. But, and that was sort of like, oh, window design matters, how you design your windows. I took the FIAS training in 2010. This actually is Jesper. Jesper was in the first. He's up there. So he was the first training class in all the United States, right?
Yeah.
I think so. This is this crew out in Illinois. And I still know, about half of these folks are still all around. Like Mark Rosenbaum is off in the corner, Paul Eldenkramp from Boston. There's Katrina Klingenberg. There's all these folks who are all part of the sort of low energy geekery thing. And in the training, you see all these products. You see all these things that you've never seen before of these German products, like this is a graphite brick tie. Low conductivity brick tie. Because it's a wick that goes right through all your extra insulation. So they made them out of graphite. It's like, And there's all these companies you've never heard of, like Shock. And here's a brick ledge that has a nylon spacer up against the building as a thermal break. And they're doing their best to do high structural loading thermal breaks on brick shelves, which are long, continuous ribbons through buildings. Fabrica makes a nylon plate that's designed to bolt between two pieces of steel to break the conductivity. So for your canopy or your tabs that are on the outside of your sunshade. And so we got to see this library of all these products we hadn't heard of. And they, in Passive House concert, they love to show Gene Gang's Aqua Tower. Because someone went out and took thermal pictures on a cold day. And the precast concrete goes in to out. It's a continuous pour. And that's a radiator in Chicago. And in Passive House training, they say they could have used this. This is the Shock Isocorb, which is a rigid EPS with stainless rods. Remember, stainless is like way down on the conductivity. It's way better than carbon steel. And you cast that into your cantilever balcony, and that sits under your door, and it completely breaks your balconies off the building thermally. And you put that in the formwork. And so we saw things like this in training, and the instructors were like, why doesn't anyone know about these things? This is our first certified house, which is a house down in Southern Virginia, which is a big, luxurious house that the owners wanted to be Passive House. I bring this one up. We got fully, this is a slab-on-grade building where foam wraps all the way underneath the whole thing, and every bit is detached behind the stone. It's like, we really worked really hard on this detailing because you have to be able to show them this continuous ribbon. It was 2013, so we were like, oh, here's our wind girt up against the curtain wall. The bolt goes back, but the bolt doesn't go all the way through, and we rigid. Like I feel like we were kind of good about the details. We figured out how to do pretty well thermally broken details. There was no steel going in and out, even though we needed steel. Until we had to tell them to cut apart the steel frame and go buy some Fabrica thermal brakes because we didn't see on the drawings that the garage of the house was connected to the steel frame of the house. And it went right through the insulated line, right through there. And it was one of those architect things where we cut sections, but you never cut sections through members. So we didn't catch it on the drawing. It looked, if it looked, we should have looked down and seen the whole frame was one thing, but it was amazing to me. I went back, it's like, why didn't we see this? We had all these sections to the building, but it never cut through that joint until we walked on site. We're like, oh, that's not gonna work. And we found the Fabrica thing and we paid to have it put in the building to get it certified. It's actually really cool. It's like these nylon sleeves that the bolt goes through there. And there's these nylon washers, so the bolt is isolated from the nut, so the bolt doesn't touch the plate. It's surrounded on all sides. It's really ingenious. But, all right.
All right. Guess I'm up.
Yeah, you're up.
All right. So, so Jesse started with 1992, and I was just thinking when Jesse was going through his whole thing and what it did to him. how deliberate he's been about it, and I haven't been that deliberate about it. I was obviously not studying building science here. So the way I got into construction was in '97 when I moved here. I didn't have a green card, so I couldn't get work, so I found out I could get paid banging nails, get paid under the table. So kind of random how I got into it. And I found out I just like to build houses. I liked at the end of the day to see, well, that's what I did. I used to do social work where you don't really ever see it like that. So, I stayed with it after I did get my green card. I got married, and I worked for another guy. Eventually, I started building on my own, doing like small hippie-like cabins out in the woods for people up in Western Maine and stuff like that. And then feel like, I had common sense. I was thinking about passive solar, using cellulose insulation, framing my stuff 2 foot on center, but that was kind of about the gist of it. And then in 2006, 2007, I spent a year in Denmark, where I'm from, with my family, and one night at this bachelor party, I ended up sitting next to somebody who worked at the Technical University in Copenhagen, and he told me about passive houses, and I kind of, luckily it stuck in my mind, but I was kind of like, yeah, this guy was really drunk probably. Well, he was definitely drunk, but it turned out he was telling the truth about these buildings, and I was just like, man, if you can build a building for almost the same price as a regular building, and it uses 90% less energy, it's more comfortable, it's healthier to be in, why would you not do it? So I was like, man, I'm going to go build some passive houses when I go back to the States. So I came back to the States the next year, and there was like nothing going on, it seemed. There was like, there was like the stuff out in Urbana that Jesse talked about, but there wasn't much going on in the States. So I kind of had to, I'm not an engineer or an architect. I'm a builder. I'm not even trained as a builder. So it was kind of like random that I ended up, having to be certified as a passive house consultant to find out how the hell you build these buildings. And it took a while for me. It was right when the economy tanked, so I ended up being gone for a year to Denmark. So business kind of took a hit from that. But 2010, I got involved with this project down in Lovell, and it's not a passive house, but it has all the components. It's a SIPs on it's a floating slab with a timber frame wrapped in SIP panels. It's fairly airtight. It has the heat recovery ventilator. The passive solar gains could have been optimized more, but it's pretty close. And then finally in 2012 we finished our first passive house. So it was kind of random that I got to it, but now that I'm building these houses, I hear from I get really positive response from the homeowners. They love the houses. They love that they're not really spending more money. They're spending more money on their mortgage, but they're saving the money on the energy. So, their monthly expenses overall are the same. And they're getting, the higher comfort, the healthier house, it's less affected by changing energy costs. So, my subcontractors who come in, they're always kind of like, so what's going on here? And like in the beginning, they're kind of curious, and they're like, well, why are you building these thick walls? But then as they're in the house and they feel how the house is performing, we have 1,300 watts of heat in the house right now that we're building, and it's totally adequate to heat the house. It's like a 2,000 square foot house. So you should really get on the passive house bandwagon, because that's where it's going to go. And if you don't, you're going to be left in the dust, I think. So I'm just going to go through some projects that I've done in the last couple of years, and I'm not going to go into details with every project, kind of picking out a couple of details from each project, but I think I'm kind of hitting most of the important things. And so this is our first house up in Uri by Sunday River. $146 a square foot, not including the groundwork, but the septic system, but like for the entire house, the porches and everything. And I calculated that's about 6% more than it would have cost me to build the house as a regular 2x6 stick-framed houses, which is what I used to do. Hopefully you didn't come here for my beautiful drawings. So just to give you like a little idea about what we did, the owners came to me. They knew they wanted a passive house, but they already had a design for like what the house should look like, and the designer really, I was all like, let's do like floating slab, TJI walls, the whole thing, and he wasn't really key on that, so we kind of ended up with, I think Jesse calls it the passive house on training wheels, where you kind of go for it, but you're also kind of holding back a little bit. So we have a traditional frost wall, sits right down the ground, and then we have a slab inside the frost wall that's thermally broken from the frost wall. Then have double stud wall on top of that. And I don't want to get into this whole talk about dew points and stuff, but I guess the rule of thumb that I've heard is that to avoid any kind of condensation in the wall, you try and keep your inner air barrier within the first third of the wall. So to avoid having our air barrier go all the way to the outside here by the floor joist, we ended up having the floor joist resting on the inner wall, which gave us now, we have this wall which is carrying the load of the floors, and the outer wall which is sitting on top of the concrete wall that's carrying the roof load. So that made it a little complicated, but you can see we have our plastic underneath here. High quality, you don't want to just pull off like the 6 mil plastic from the lumberyard, get something thick. It goes up, it wraps under the plate, goes in on the wall here, connects to the windows, go back up around my floor joist, goes back up to the ceiling, and then connects across. On the outside I have a wind barrier, so like basically your tie pot, but rather than just slapping the tie pot on, taping the seams and trying to pay attention to the connections and make sure you get everything sealed up. One thing I guess is to avoid wind washing, where the wind penetrates the weather-resistant barrier and kind of lowers the R value. But the other thing I'm also thinking is, if the outside is super tight, if I have a hole on the inside, it's going to matter less. So here's the frost wall. The lowdown on that is to make these chamfered edges, you end up cutting a lot. It's time consuming. It's kind of a pain. You end up with all this cut foam everywhere. It's hard to lay out the plastic on top of it and to get it to really follow the lines, especially in the corners where you're coming down with chamfers on 2 sides. When the concrete guys come out to pour, because it's a finished concrete floor, they don't want to pour in all one pour, because the 10 inches is going to cure differently than the 4 inches of concrete. So they pour first the thickened edges, and then afterwards they pour the entire slab. We fill it with wire mesh. And I heard somebody say the other day you always get cracks in concrete slabs, and that's not my experience at all. We put rebar in the load-bearing parts of it, and then wire mesh everywhere else, and it stays together well. But it's a little bit of a pain to do it, but it worked out pretty well. Houses stick, the double stud wall with plywood gussets keeping it together, and you can kind of see the plastic that's going to get attached to the interior air barrier is rolled up on the inside of the house. And on the outside we attach another layer of plastic just so we don't get moisture wicking up through. So this plastic here that's hanging out here is actually attached to the inner plastic, and it comes out under just so we're not getting moisture wicking up either through the concrete wall or through that insulated space between the wall and the slab. This is the interior wall. So on the inside of the wall we have OSB with all the seams we use to prime them and tape them. You can see my plastic coming up in here, and that then gets taped to that barrier. We put a little piece of foam down here with a 2x4 on top to try and break the thermal conductivity of the plate below it. I don't really know if it's worth it, but I'm kind of going for everything here. And then we end up with this wire chase in here where we can run all of our wires. An 1.5 wire chase is really small because the electrician needs, for his boxes, needs a certain volume for all his connections. So they end up using these oversized boxes that they then reduce on the front. So another thing with the with that double stud wall, that was like a little composum or whatever you want to say. So this is like a penetration to the outside. We put it through a PVC pipe, tape it up, fill with spray foam. That way, if you have to do something down the road, you can pull it out through the PVC pipe, shove in the new wire, foam it up again. View from the inside, you can see the window bucks built out here, and up there you can kind of see this little shelf that we built for the floor joist to sit in to try and keep that airtight connection. And you know, just because this is now coming up, it's joining up with the subfloor up here. So it's taped here, it's then taped again down here, and that's just, it's like I'm glad I was there all the time to really keep an eye on it, because I would be a little nervous about just having some guys out in the field and just going to town on it. So you need some adult supervision with that detail. Part of the roof is rafters, so we're using TJI rafters, and then because we could only get 16-inch rafters, we then build them out to 24 inches. Just scab on some 2x4s in the bottom and fill it all up with cellulose. So to keep this open vapor diffusion wall system going, where you have, like, you know, on the inside you have the OSB, which has a very low perm rating, so moisture won't go through it. On the outside you want to have something with a very high perm rating, so we're using this fiberboard like Jesse mentioned earlier with tie power over it, and it just took forever to get it. So, you know, normally I would have framed my walls on the ground with the fiberboard and the tie power on it and then stood them up. Now instead we end up building the entire house without any shielding, and I'm sure everybody was talking about what a bunch of idiots we were, but we just didn't have the material there. It's one little thing. On our rafters, we ended up putting 1/2-inch OSB on top, and then we strapped that, and then we put 5/8 plywood over that to vent the roof. So rather than venting the roof with, like, you know, rafter vent or something inside the actual rafters, we did it kind of on top of it. And then trusses, it's the other section, very easy. Finally, we got the fiberboard on, and I kind of like this kind of modern look, no overhangs and all black, but that didn't get to stay. So the fiberboard was really temperamental too. This is the day after we put it up. There was like a little sprinkle overnight, and there was one place we'd forgotten to nail it, and it just swells right up. And all over that building, when you were looking at it, you could kind of see like these bows in it. Luckily, we had a rain screen on the outside. So, you know, it did get furred out, but it definitely gave me like a little, made me a little nervous. And you can't stable anything to it. You can't stable your tie power. You have to shoot it on with a button nailer, which I didn't have. So we ended up putting our rain screen on to hold it in place. And you can see how we shot it around all the windows and stuff. And then later on, when we put the windows in, I was like, damn, now our flashing won't meet up with a weather-resistant barrier, so we had to peel it off on top of the windows again so we can get the flashing into the weather-resistant barrier. And then rather than cutting it and tucking it under, which is the typical detail, or the normal detail for me, it used to be anyway, we now tape it with flashing tape so that that weather-resistant barrier can stay intact and you're not slicing it to get your flashing underneath it. Sealing inside. Kind of a funny little story here. We used primed the edges and used Kruse Vicor tape, and then after about a month we noticed that it was kind of starting to let loose. So then we're like, well, it must be because it's really cold. So I got the iron that I used to wax my skis, and I brought it in and had one of the guys like iron the entire ceiling. But that eventually actually, you know, it held up for a little while, but then it gave in again. We ended up putting plywood strips over every single piece of tape and then screwing it in, which was a real pain. Luckily on the walls, we hadn't done those yet, so at this point we figured out we should use zip tape, which worked a lot better. So here you can see the, the zip tape and then the strapping on it. So Over the windows, because we had those big frames, we over-insulate so it's not, actually we're insulating this partition in here, but you can see over here, we're kind of trying to over-insulate the window so we don't have so much exposed frame. And this is why you should use open web joist for all your ventilation duct and stuff. It just makes it so much easier for everybody on the job site. All my subcontractors love it. It's like night and day compared to like TJIs. They have knockouts, but it never works. Open web joist are definitely much preferable, I think. All right, we put in temperature monitors. We got Barry up there who's commissioning the ventilation system, and we bought some old meters from CMP, put them in, and then we're running all the hot water heat, all the heating for all the electricity to run the hot water heater, which is inside a solar thermal tank. We're monitoring that, and we're monitoring all the electric heat as well, which is, there's also a wood stove in here, but which we can't, I mean, you gotta look at how much wood you're burning, but the electricity we can actually measure. Solar panels, and you know, I think the whole thing about renewable energy is how can you have any pudding if you don't eat your meat? You know, you gotta do the hard stuff first. Insulation's really cheap, air sealing's cheap. Concentrate on the envelope, lower down the amount of energy you're gonna use, and then after that, you get to put on your fancy renewable energy. And we've started now putting permanent roof anchors in, just because you know somebody's gonna be up there messing with something. So put it on, it costs like 25 bucks, and it makes everybody happy. Access to the attic, we do that from the outside with a little hatch, and then we try and air seal that, just rather than having, you know, you can't really have an attic hatch on the inside of your house going up through like 3.5 feet of insulation. So that's just an easy way to do it. You got a little ladder, you get up there. Put a catwalk in there. So we built the catwalk up at 4 feet. We basically fill up that whole attic with insulation. So if you don't have the catwalk and somebody needs to get in there, you're just screwed. So that would be a good thing to specify as well. So we use the wood stove to heat the house, and we use these Envy heaters, 130 bucks a piece. They just look a little nicer than the ones from Home Depot that Jesse showed. And they're great, so that just gives you like a little control in each bedroom. So if you have grandmother over and she wants it really a little warmer, you can turn it up there rather than, you know, having to heat the entire house up. And the jury is still out on the wood stove. It can definitely work. You can kind of see we have dedicated air source underneath. Can't really see, but it's right down there under the wood stove. And it's not hooked up, and the reason is that the wood stove, although it says it's airtight and it has a dedicated air supply, the air supply comes up right next to the wood stove, but it doesn't to the firebox, but it doesn't actually connect to the firebox. So if we hook it up without a damper on it, we're just going to have this 4-inch hole to the outside that's going to be open at any time. So once I get my act together and actually find a damper, we can put that in, hook up the air supply, and hopefully it'll work better. But the wood stove, I love the idea of a passive house with a wood stove, but you need to be kind of careful. Be careful with combustion and the ventilation system not sucking smoke out of the wood stove, you know, killing everybody. That would be pretty bad. So be careful. So, you know, thickened edges, not a big hit, but the quality assurances I really like. It was cool to know that the house actually performs the way it's supposed to be and have it checked. And I couldn't figure something else out to say about that. So the owners, total tree huggers and doing it for all the right reasons. Whereas the next house here, this family's house burned down. They were under contract to buy another home, and the wife just didn't want to move from the land. It's beautiful old apple orchard. And so kind of behind her husband's back, so to speak, she came to me, and she just saw the sense in building a passive house. This family is like tractor driving, hunting, you know, local people, not your typical tree hugger. They just see the sense in spending your money this way. So 120 bucks a square foot, I think that's pretty good for for a nice house like that. You know, it's not like Taj Mahal, or there's not a lot of fancy details, but you know, you can definitely build it without killing the bank. So this time we had, it has a full basement. So am I doing on time? Am I like, sorry, I just got to check here, make sure I'm not way off. So, so we basically poured a typical 8-inch wall. We put foam under the footers, put foam under the slab, and again we put our airtight barrier starts out on the way inside because we just taped the EPS sheets of foam, figuring we could use those as an air barrier, and maybe somebody's like, all kinds of stuff can travel through that. I actually honestly don't know, but I assume it's okay. So we put, originally I just wanted to put all my insulation on the inside, and then when I started researching it and talking to other people, they were like, well, if you have any kind of air penetration and it goes through all that insulation, it's going to hit this freezing cold concrete wall, maybe it'll condense. So that's why we ended up putting some foam on the inside, but the bulk of it on the outside. And then we switched over the wall system to now having a 2x6 wall. Again, back to the old familiar. And then on the outside of that, we're bolting TJIs. So we end up with a 2x6 wall, obviously not to scale here. So 2x6 wall with plywood on the outside where all the seams are taped, so that ends up being my airtight barrier. Then I bolt a TJI on to the outside. My floor joists can sit. So the framing on the inside of the house is the same as it used to be. You know, it's really easy for my electrician, for my plumbers. They can just pull their wires through this wall like they normally do. No questions asked. It's just going through this plywood to the outside that I'm now concerned about with my subcontractor. So, yeah, we actually did that. Put foam under the footer, which kept me awake at night. But I met with an engineer. We calculated it, and it's going to hold. And the house is still standing, but it's definitely kind of counterintuitive. So you can see we're wrapping everything in foam. We put down our pressure treated plate to the wall, and then on top of that we put these strips of plywood. So we have something that we can tape the foam in here to that plywood, and then when we're building our wall that will sit to the plywood, we can tape that again, so that will connect the air barrier from when it's jumping from the inside to the outside of the 2x6 wall. It also keeps dirt from getting in behind the panels when it's getting backfilled, because this was all on before they backfilled in there. We put these small blocks on to keep everything in place, and then afterwards we just go in with a spray foam gun and we just spray foam this little gap in between here. But all this foam you order, well, I order it from Branch River Foam down in Rhode Island, and I tell them exactly what sizes I want for sheets, maximum 4 feet wide. I think you can probably get them just about as long as you want, any thickness, and I just kind of figure it out as a puzzle. So when I get my pieces, I put it all together, and I know that that last piece that's like 2 foot 3 inches and 2 foot 3 1/4 inch goes in that last corner. It all fits together, very little waste, unlike the thickened edges. Now my wall, I'm just stick framing it on the ground like I normally would. We tape the seams, we stand the wall up, frame up the next wall, tape the outside corners afterwards, tape the connections between the first story and the second story, and up it goes. So at this point, it's like nothing's really been new or exciting, so to speak, you know, besides the foundation was a little different, but the wall, we just taped a whole bunch of stuff, and that was basically it. And you might think, oh yeah, that's great, you're taping it, that's going to last like 20 minutes. So I got my best man on the product testing. My son had a rip in his snow pants. We put a 1/4 inch strip of that tape on this big tear he had in his pants, because he's really picky, you know, he doesn't want like big pieces. So that was 2 years ago. The tape is still on. This kid is like penguin sliding, skiing. This stuff does not come off. So you don't have to have worries about taping stuff, you know, because it might seem like it's kind of lame, it's not going to work, but it definitely sticks. So we take these TJIs, I order them in whatever length I want, cut them to length, put them on there, and we snap a line where our framing members are, and then we just put the TJIs on, and we bolt through the flanges, opposing sides every 2 feet all the way up, and it is super rugged. Here it goes all the way up, and then afterwards, again, the tie bar and the fiberboard, which we ended up using again, not really because we wanted to, because we didn't really have anything better that time. When we insulate it, we just cut a hole in the airtight barrier, so now we're making all these holes, which is great. Then they shove their insulation pipe in, dense pack everything with cellulose. When they're done, and after they've drilled holes everywhere else to make sure that it really is dense packed, you know, way down the basement, they were down there drilling holes and checking, and we really didn't find, we found one place where it wasn't packed really well, and then we fixed that. But we just put construction adhesive over that, little patch of plywood screwed in. We imported windows from Denmark, Ecliptica windows, for this project. You know, gives me a chance to go to Denmark and write it off as a business expense. The cool thing about these windows is that the frame is extremely narrow, so even though the frame is not as well insulated as some of the windows Jesse showed, we're actually ending up ahead because it's so narrow, plus it kind of looks cool. I think you're getting more sunlight through it because you have less frame, more glass. It's one thing kind of never thought about, but when you have this TJI wall on the outside or foam, you need something to cover that foam. You know, you have got foam or insulation down here, so we've been fabricating these thresholds out of steel with like little flange that goes up to the inside so we can screw it in to put the load onto the TJIs, or the framing instead. And one day you can probably buy them pre-manufactured, but we're having them made up, and it's like almost $500 in the latest project, so it's a little expense. We put in Mitsubishi mini split this time, and that heats that entire house, 12,000 BTU for a 3,000 square foot home. So I just wall, mini split, yay, and the fiberboard gets the thumb down. Oh, and just one thing that, I don't know if Jesse mentioned it, maybe I wasn't paying attention, but the whole thing about the Passive House is to try and make it durable and resistant as well. And one thing we started doing is putting grates into decks just so it's not like dripping right down on the decks and splattering up against the buildings. All right, so this is actually my own house. We bought, this is 14 years old now. 13 years is what a Brosco window will last when you paint it like I do, which is probably not that much. So we've been wanting to change stuff in the bedroom. We knew, in the living room, we knew we had to get new windows. So I was importing these windows for this other job anyway. So I was like, well, let's get some windows for this house. And then afterwards I was like, damn, well, I can't really put triple pane glass windows into my lousy 2x6 wall, so kind of got roped myself into doing an interfit, which is basically bringing an existing home to the Passive House standard. So dug down to the footers on the outside, added a whole bunch of foam that's under this top paper here. Then we added a new airtight barrier. Ran right over the windows, reframed the windows to the new sizes I wanted, ran the airtight barrier over it just so mosquitoes and rain wouldn't come in, because we're still living in the house while we're doing this. Then after, when we're ready to put the windows in, we cut out this is then the DA barrier it's called. It's made to go on the warmer side of your wall assembly. We fur it out with plywood, and we then put plastic over that. So that's my temporary window. So this obviously works better in the summer. And want to remind the contractor to add the extra inch for the rough opening, because on my very first project when we started doing stuff like this, I didn't, and we ended up spending a lot of time changing the window openings. So afterwards we just bolt this TJI on, and away we go. And then we put our, so this time we finally got rid of the fiberboard. We get this Mento Plus barrier from 475 down in New York. And you can get a similar product, Sega product, through Maine Green Building Supply. And it's basically a membrane that does what the fiberboard and the Tyvek used to do. Tape the seams. This can handle like a 38-foot column of water. You can actually, they have another product that you can basically leave exposed. This can be exposed for up to 3 months, and then the UV will start breaking it down. Cut around the windows, tape it to the window buck, put a clapboard down there. We always put clapboards in to kind of get the water in the window to drain out if you get water in there. And I think the whole, just to go back to that whole thing about the moisture, people seem so obsessed with dew points and moisture getting into the wall. And I think when you get moisture into the wall, 99% of the times it's because somebody screwed up a flashing detail or something's messed up and you get rainwater in there. So the clapboard, you know, and then wrapping that in ice and water shield or something so you have a pitch going out, I think that's kind of more important. So we just cut a hole in this membrane, insulate through that, and then afterwards we tape over it. And now I actually got 6-inch tape, so now I can do it all with 1 strip of tape rather than 3. And then it gets this kind of complex board and strapping system on the outside to create space between your siding and your membrane, just so that the insulation, because this is obviously a very soft material, it's reinforced, but as you pump it full of cellulose, it's going to want to blow out and touch your siding, so you get these battens, flying battens that you put in to make sure that doesn't happen. We've got our windowsill with a metal sill in it. Pop the window in, we screw it through the jamb for this fixed window here. Cool little thing you can see in that top photo there. We get these small color-coded plastic shims with barbs that I buy when I go to Denmark on these business trips. They're just awesome because rather than using paper cedar shims, which is what we used to do, slide them in and then you got to cut them afterwards. These are so slick, they're real narrow. You push them in, click them together, and then afterwards you can spin them, so you just have this narrow little thing in there. It doesn't really conduct cold through it. The windows get taped to the window buck, you know, to make the airtight barrier after you spray foam in there and all this other stuff. So for the ventilation system, so what we're doing is we're just doing one wall in my house, and then the idea is that we're going to go all the way around. You put these Lunas ERVs in, which is you drill a hole in the wall, pop that unit in, drill another hole somewhere else in the house, pop that unit in, connect the 2 units to a power source and to each other. And what they do is they work in tandem, so one will pull in air and the other will exhaust air, and then 70 seconds later they'll switch around. So that's how they do the airflow without running ductwork through your entire house. That's what it ended up looking like, kind of rustic reverse board and batten on the outside. And then I used some old slate pavers that we screwed into the bottom of the frame and used that to cover the foam we put on. So very happy with the windows and the Mento Plus. Oh, and I just wanted to say, oops, what Jesse said about the comfort. My kids are sitting in that big window all winter long, using it as a couch, sitting with their back against the glass watching TV. It's really the comfort issue. I can't stress it enough how it's huge selling point. This is the house we're working on currently. $157 a square foot. The owners in this, I think, are just kind of seeing the sense of it and probably got a little bit of tree hugger in them, but mostly I think they're just this is a great product. Finally got to do my slab on grade. Had to build it up quite a bit to make it work in this location, because it had to work with the septic system, and the whole area was kind of messed up. But after 100 loads of gravel, we got to put it out. So this time what I did is I just got 8 inches of reinforced concrete. Rather than doing the thickened edges, we just did all 8 inches everywhere, which was so much easier to lay out the foam, one pour, work out really well. Here's the house, 2x6. Got to look for shiners, you know, all the nails that are shooting into the framing that are missing. You can see there's like a whole row. It looks like somebody hit the house with a buckshot, so we've been taping up everywhere. And you can see all that plastic that's going to get taped to the OSB barrier hanging out over there, which will then get attached. And then we're putting some more of this Mento Plus barrier. We're then taping that to the OSB again, wrapping it out over the foam, and that will then eventually get wrapped up over the other barrier and taped, so we're getting these really good seals on the outside as well. The same thing's happening up onto the trusses, where we're having a membrane that goes over the top of the TJIs and gets taped back in again. I think a lot of times people are like, well, this is costing like, you know, so much money. So this is just under $3,000 worth of labor to put all the TJIs on, and about $2,500 worth of materials. We did this south-facing wall and the north-facing wall in one day. So it really doesn't take that long. So here you can see all this complex strapping we got going on. And you can see actually on this wall, again, the strapping ended up coming right down to the top of the window. So again, we had to peel that damn stuff off, patch it up so we can get the flashing back in there. So hopefully on the next house we really get it down. It won't happen again, but a little funky. And so here on that side we had it loose, and the other ones we left the battens loose over the window so we could slide the flashing under and then tape it. Unfortunately, in a couple of places we forgot to nail it after we put it on, so when they came in to blow in the cellulose, it blew it all out. So then we had to cut it open, get the cellulose out of the way, to stable it, to tape it, to put these back on. So minor setback there. So I haven't talked about the ventilation systems much, but we're using a ventilation system from Sender, a Dutch company, and what we have, it's really nice because it has that flexible ductwork that I think you saw when I did the open web joist thing, but it also has a ground loop where you can add a ground loop to it. So we're adding 300 feet of geothermal piping, putting it in the ground, filling it with glycol. That gets pumped by a little pump through this white unit here. Has an air exchanger, so it sucks the air from the outside, pulls it through that air exchanger, preheats it with that glycol that's buried in the ground, and then it goes into the unit. So it preconditions the air in the winter, and in the summer season it will start running again when it's over 77 inside the house, and it'll actually start cooling the air for the house and dehumidifying it, which it's about a $2,000 upgrade, but I totally think it's worth it. So here's the pipe. When we're digging the well line, we just dig the well line down 6 feet instead of 4, and then we just throw it in there, and that's it. The lavender color there is just water resistant sheetrock that we had left over, so that's not staying, don't worry. And then this is our 1300 watt heater that's heating that entire house. And that's where the window is cracked right now because we're trying to dry it out, so it really doesn't take much. And air source heat pump again, the Mitsubishi mini split, and electric radiators in the bedrooms to heat the house. So I just threw the Sender HRV on here because we really like it, and the 8-inch solid concrete slab is definitely a big hit. So key lessons, you want to do this together, Jesse?
You guys will do it in the dark.
In the dark? Wow.
Hour and a half, yeah.
So I put this up for mine. This is like my top 3 lessons. Do the I-joist wall with the weather-resistant barrier. Don't be afraid to build on the foam. And certify the house. Because getting it certified, they'll find all this stuff that, well, on my project anyway, they found a lot of stuff that I hadn't found. And it's just nice. If you don't do that, you might be thinking you're doing everything great, and you know, all kinds of stuff could creep through. You want to see what you got in there, Jesse? Or?
Yeah. Can you guys take a few more minutes, or should we move to questions? A few more. So, this was one that came to us for a little while, which was, when you're doing a passive house, everyone obsesses over this heating number, and you end up like gaming the spreadsheet trying to drive it down. And we've been getting told by a bunch of people, you need this to certify, but the real big deal is the total energy we all use. It's not how much we use for heating. It's the total package. It's your total damage. And it's like, I think it's because they gave you 2 decimal points that we obsess over 2 decimal points, but we probably shouldn't be. And most of our buildings don't meet Passive House. We, I don't know, 1 or 2 a year. So instead of 4.75, we do a lot of houses that are 10 or 11. But they meet the overall number, the total damage. And you know, we got various reasons for that. So this one, we decided in our office was more important than this one if we had to give one. What else we did? Oh, Jesper said this. Air tightness is actually really cheap because this is labor and this is skill.
Right.
This is caring. It's not like, you know, builders actually often underprice this their first time because they're, you know, they don't want to admit they can't do a super airtight building. So they'll often give this for almost nothing, but it turns out not to cost much. I mean,
It's like
if you're trying to value it, is this
spent like $1,000 in tape probably. Like I probably spent like $1,000 in tape, and that's including my flashing tape, and you know, you can figure out what the labor is, like maybe $1,000 too, but
and
it's not much.
It's really cheap when you tell a builder who hasn't done it before that someone they're competitive with has done it. And that's when it gets really cheap. Mike Monahan did a .4 ACH 50 building with us because he was, by God, not going to get beat by his right run.
Yeah.
And it was, you know, that was all it took. And I don't know if he's ever done it bothered since. I bet he hasn't. But, you know, he beat the Passive House standard by 30% just because he was obsessed. You know, he was getting competitive over it. So, passive houses in Maine use a lot of passive solar energy. You've got to do a shading study if you want to certify your building. And what that means is, how many trees are actually, you know, when you do a model, you don't really look out the window and count trees. And the sun, if you're building a rural house in Maine, there's usually trees all around it, and the sun, it's probably not as passive solar as you think it is.
Right.
And so the solar guys will come out and they'll do the solar shade study, and then you count up all the shadows and you put it in your model. And it's, or you can then use it as a clearing device. You can sit there and say, cut that one tree down, please. That's the one that really matters. If you're trying to certify, you really have to do this early, or else you will get lots of bad surprises in the end.
Yeah.
And that was a big one. This was one. So passive house and passive solar. The two are entwined in very interesting ways. One is that this is a solar map of the United States, and this is how much sun Germany has. The only place in the country with that bad sun is Seattle and Alaska. We are way, way, way sunnier. So, like, we're Spain in terms of sun. Maine is a really sunny place. Down here, it's a whole different category. Europe doesn't have anything like this. So the Germans developed Passive House for this climate. You take what they do and you drop it in Seattle, it works perfectly. If you do it here, the R values don't line up. You're like, why does Germans only have to do R40 and we have to do R80? And then you say, why does Jesper and Geologic only have to do R40? And the difference is that the Germans go for this balance, but in Maine, if you're building a single family house in a field, you can really crank up the passive solar dial. So you can put a ton of windows in the south of your house, and you will get a bunch of free heat. So your heating energy will go down, and then your R values can come down. This is, but you know, like when you go to the conferences, there's all these guys who are like, yeah, we tried that in the 70s too.
Right. It overheated, but.
And they overheated their buildings, and so it can get risky. In other words, that you're sitting with this spreadsheet and you're trying to drive down the number. That's the game, right? It's very video game-ish. You're like, oh, I'm at 8. What do I do to get to 4.75? And you add insulation, and then you start adding windows. And, you know, that will work. But if you do that without thermal mass, I mean, the old solar rules. You do it without thermal mass, the building will overheat in October.
Yeah, you definitely mass big time.
And so the trying to get to the number, you will take advantage of the amount of sun you have. And that can get really risky if you've got an apartment building where half of it faces south and the other side faces north. I mean, is that a passive solar building if half the apartments don't even get that sun? You know, so you get into these weird things of, because we're so much sunnier, but we're also so much colder. So we have more free energy, but we're colder. The easiest way to get to Passive House in Maine is to do a really passive solar building. And the ones that have been done are, for the most part, very old-fashioned passive solar buildings. But there's some risk in it. And the Germans look at us and say, you're crazy. This is safe. 1/3, 1/3, 1/3 is safe. So that's something that we've been kind of catching on to ourselves is, you know, what's it? And you have to start asking your client what it's like to live in. And I had the same thing, certify, which is certification taught us. It doesn't matter who you certify with. Certification teaches you. And it holds you to the fire. It's just like LEED. You know, it stops backsliding. It stops like,
Well, see, I think like if you certify one project or maybe two, then it's like you find out what's going on. So, you know, I don't know if you necessarily need to certify every project.
No, but certify one.
Right, at least one, yeah.
Do one,
Right.
and you know, get someone who wants it, and then you'll really have to do it. And then, you'll only do one every 5 years.
Yeah, right.
But you know, then the other thing, like once you have one certified, you get lazy. So you probably have to do one every 3 years to keep yourself honest, because then you'll start backsliding because you're human. And if you're going to certify, design your building to be a 4.0 building, not a 4.75 building. Your first one, because you will find things and it will creep up, and you will end up at 4.74.
Yeah.
By the end of your certification.
Exactly.
Yeah. And so the other lesson is, all of those people who you pay to certify will pre-certify. They look at your design drawings, they tell you how you're doing, and then they tell you all the things you did wrong, like you put the French door in as one window. Like, oh yeah, French door, it's an 8.0 by 8.0. Well, no, it's actually two 4.0 by 4.0s because there's frame that goes around. Is if you don't count the frame blocks sun, and you can't count that free heat that would have come in. You can't pretend that, you know, don't ask us how we know, because, you know, certification caught that. This is one we put in. It's like, you got a really good budget, you can do this. I mean, Jesper's doing it for like $120 a square foot. So if you've got a $250, $300 a square foot budget, you can pull this off.
I think so.
You know, it's like, keep learning. This is one. Like, we didn't make any of this up. We are just architects in Portland. We learned from other people, and here's the Maine Green Building builders.
Yeah.
What do they call it?
Science.
Building science discussion group. I mean, you know, look at all those people who are geeking out on buildings. That's the Passive House Maine group at one of Jesper's houses. This is the Nessie folks. These have been, I mean, it's hanging out with other people. And I think the really interesting thing is there's this funny human thing where you start getting competitive. You're like, oh, so-and-so did one. I got to do one.
Right.
And that's good for you. It's good to be competitive.
And there's so much stuff online. I mean, if you can read and you have internet access, all the information's there.
Which we think all of you can.
Right. Pretty good hunch. Yeah.
So that was it. And these are all the various groups out there who are all talking about this and trying to figure out how to do this affordably. I think that's our entire show.
That's it.
All right. It's dark. All right, it's late. People have questions? Everyone go home?
How did you normally break the chimney with the wood stove?
Well, I guess we did. What we did, it was like a metal Vestas chimney. So up in the attic, we sealed it with high temperature caulking to a piece of sheet metal. So we air sealed it, and then we took totally illegal, of course. We took a 14-inch piece of metal duct or culvert, and we ran it over the chimney, and then we filled it up with rock wool all the way up to the top. So, I mean, I'm sure there must be some thermal conductivity going through it, but you know, it's also filled with.
Or you over-insulated the chimney, the pipe.
We piped it right in next to
Yeah.
the chimney, which you're not supposed to do, but I didn't tell anybody, so.
Did you thermal break between your I-beams and your main structure when you were bolting them on?
No, so you do get some thermal bridging, which is taken into account at the PDH, the software program, but so you have a 2x6 half-inch piece of plywood, and then you have 12 inches of a 3/8 of an inch strand. So it's taken into consideration if you go in with an infrared camera, you can actually see the TJIs, but you know, at that point you're still having like R, you know, 25 or something like that.
So you can see a little light line
Yeah.
from the web?
Yeah.
When you put it in the software, it's almost invisible. It's like it doesn't
Yeah.
count as a bridge.
No, but you
Because
still,
it's raised, but
have to
it's
take
a
it into
little degraded,
consideration,
yeah.
right? Because it's not insulation, it's
wood.
It's wood.
Yeah.
So
Yeah.
When you put those on, they don't bear anything? They're actually, the 2x6 wall is supporting?
yeah. So on the first house at West Paris House, we were nervous about that. You know, whether they would actually end up sagging. So we put that inner part of the web to rest over the foundation wall, and then up where the joist met up with the trusses, we then tied that in with a half sheet of plywood, so it would kind of like hang onto it. But honestly, after you bolt that on, and I'm just like, man, this is so rugged. I was just like, I'm all right with it. It can hang right off there. I also reinforced where I put in the decks. You know, they're now hanging up the TJIs. I reinforced that with 3/4 inch plywood. But just after working with it, I'm just like, I'm convinced it will hold because it is super rugged. So
And you talk about that. The thing that everybody likes is that there's an inside of the house and an outside of the house.
Yeah.
Like the subs can all be working inside while the framing crew's working outside, and
Right.
nobody's in each other's way. It's like it used to be.
one, it's just like, they can run their wires. The plumber can run his
They can drill any holes they
stick
want.
pipes and through. It doesn't matter because it's still, you got like another 12 inches of insulation on the outside, and they can run all their stuff through. They're not going through any barriers. It's only when you need to have your outside lights or your outside outlets that you need to pay attention to it. So
The interior 2x6 wall, do you insulate that with cellulose
yeah,
as well?
yeah.
But you could probably get it without it. I mean, well, you would probably need Passive House. That would probably
Yeah.
get it below.
Maybe you could, but
Yeah.
I mean, I could probably frame it up with a 2x4, but I'm just so used to do 2x6 that because I feel comfortable framing that 2
Yeah.
foot in center, and then I can get
Oh,
my
yeah, right.
TJIs 2 foot in center, so it's just more,
Because they're
It's
expensive,
less
so
work,
you need
yeah.
a lot less of them.
right, so
Yeah, that makes sense.
And is cellulose the preferred?
I love cellulose, yeah. Well, just because it's like recyclable, it's a recycled material, it's pretty natural, and, spray foam, I think sometimes people think they can just spray foam their way out of the air barrier, but as the house settles, this stuff like cracks and it's not airtight. I mean, it might be airtight for a little while, but not in the long run, so.
We've been getting these big warnings at the conferences that the blowing agents in the closed cell spray foams are such huge greenhouse gas forcing agents that they aren't, they're doing more damage than the energy they would have used with the closed cells. And then until there's some new blowing agents supposedly coming on, that the HFC blowing agents are these vigorous climate, they're like methane, or they're like,
yeah, it's
whatever,
bad
they're way worse they're 1,000 times worse than CO2. So you're getting these scary warnings that this closed cell we may have been using was, it was saving energy, but it wasn't saving the greenhouse gas issue, which is
why we're usually trying to
so
use
complicated.
EPS foam, right, rather than XPS foam.
And then you go to the conference and say, yeah, in Germany they banned those blowing agents.
Yeah, right.
BASF in Germany doesn't sell the spray foam, they sell the BASF USA. Which is like, so, and you see the German videos, they don't use any spray foam. When you go to the conferences, the Germans just don't use spray foams, they use mineral wool.
Yeah.
All the time, they use mineral wool and fancy membranes. And it's, it just looks so different than it does here.
Yeah.
Your roof venting, you said you had 2 layers of decking, or were there spacers in there for the roof venting outside the insulation on the top there?
Well, I think, are you talking about the rafters?
like in
I guess
Newry.
Yeah, we put 1/2 inch OSB over the top of the rafters, and then we ran 3/4 inch strapping down, and then we put our 5/8 roof decking over that, so the air space will travel through, under the shingles,
Right.
but not inside, where it could mix in with the insulation.
Like the old mountain cold roof that Jackson.
Yeah,
They
right.
did a lot of that.
Yeah. So if you were doing standing seam, I guess you could just put plywood and then the strapping and then put it right over.
you have problems with air quality in such a tight?
Well, no, because you have, I guess I kind of jumped over it, but the heat recovery. Oh, because you never really mentioned that in your thing.
Yeah, right. I mean, it's funny because it's not.
You
part of
have a
the thing.
balanced ventilation system inside the house that has heat recovery in it. So that unit that I showed with the ground hoop, you know, the ventilation system, you take fresh air from the outside into the house and you exhaust the same amount of stale air. And it has a heat recovery unit in it, so it takes the heat from the air that's blowing out and it's using that to heat the air that's coming in, and it's doing it with like 85% efficiency.
So it's swapping every single bit of air in the house every 3 hours. Every 3 hours it's purging 100% of
HEPA
the air.
filter on it, right? So
Yeah,
any
so-
kind of pollen, any kind of pollutants from the outside gets filtered out. They actually have really good indoor air quality
Yeah.
in these homes. I mean, much better than a conventional home.
It actually, it's sort of funny is that when these houses with these HRV, like you walk inside and it doesn't smell like inside.
Yeah.
It just kind of smells like outside. You know, it doesn't
Just
smell
clean,
different. Like
yeah.
if someone's really cooking, you can smell it, but it's
Right.
it's
What's the
funny.
brand of unit you do and how expensive is it?
Oh, you can do them from 4,000 installed to 8 to 10. So Jesper's using the Zender, which is it's Runtle's parent company, and they're down in Portsmouth, and they sell this super efficient, 85% efficient box. It's really quiet, and it's the Mercedes of boxes, and it costs $2,200 for the box, but you can get a Fantech for $750. So,
But with this center unit, well, it has a
Yeah.
flexible ductwork, which makes all the difference in the world. So you're not like taking metal pieces and, you know, putting them together and sealing and stuff. It takes me like 4 hours to run all the ductwork for the
it's
entire
a
house,
home run fresh air system.
and then it just goes back in there and you're done. You know, so-
Smooth on the inside and corrugated on the outside. They're like, they say you can clean it by running tennis balls. They have tennis balls, they blow down them. They're designed to cast into slabs. So in Germany, I think they cast them into the floor slabs. So you run it to the room and then you pour your slab over the top. And so everyone's adapting them here.
I haven't.
We do a lot of houses with regular sheet metal ductwork, and then we might do the fancy box. So the more efficient the box, obviously you save more energy, but the real deal is that an 85% efficient heat recovery unit gets the air 85% of the way between inside and outside. So, you know, anyone doing commercial buildings, they always have the post heaters because they're so worried about how cold the air is going to be blowing in. So it's 0 out at 70 in. If you're 90% of the way, the air coming into the room is 63. If you buy a cheap box, a 50% efficient box, the air coming into the bedroom is 35 degrees. It's better than 0, but it's 35, and you will cool down those bedrooms really aggressively.
Yeah.
So the Germans are obsessive about how good their units are, so that again, you don't cool the bedrooms down. If you don't cool the bedrooms down, you don't need to put a lot of heat in them. So it's all this cycle of like the
But
fancy.
then it's also like comfort, right? That you're not lying in your bed, you're not feeling this cold air, and it's almost like draft coming down on you.
I mean, I had this hilarious experience where we were working on a multifamily unit. It was assisted living, and they didn't believe our energy models, and they refused to. They had a full hydronic system. They had air conditioning, and they had a HRV in it. And I was looking at their plans, and on the plans they had these post heaters outside the HRVs. They had these little funny boxes, a little electric coil. I was like, that's the German thing. That's like in the slideshow. You put the electric unit right after the HRV to put heat into the ventilation area. He's like, yeah, well, I'm worried it's going to be too cold, and you know, the little old ladies, they get cold easy. I was like, but you can heat the whole building with that thing. And he's like, oh, whatever. So, you know, they had a full boiler and a whole full heat pump system in this building. You know, that's why it was so expensive.
Yeah.
But it was really funny to see that, like, they were doing the exact same thing the Germans did. They just had like $500,000 of extra stuff.
When you do the R value calculation in the program, we're using the same R values as we're accustomed to here. The Germans have more conservative, realistic numbers for the different installations.
They're from ASHRAE.
Are they?
Yeah, and the fresh air stuff is actually, it lines right up with ASHRAE. So they're surprisingly aligned. You know, like, I think there's some numbers that are a little off, but it's,
Yeah,
The
I
chart
mean, it
is-
says right in the,
see, they cite it, and I was surprised. Most of the citations
Yeah.
were ASHRAE.
right.
So, I think they were all looking at each other. So, yeah, that hasn't been a weird thing. It's more metric that's the pain in the neck. Not for you, though.
No, well,
Are you're now American?
well, I said, well, I'm doing it, actually, I'm doing it in Imperial unit, so,
There you are.
yeah, I switched over.
Okay.
Well, it seems like that's what everybody was doing in the beginning, and now it seems like
That's like
everybody's
going
going
back
back to the watts.
Yeah. Do you remember anymore?
Oh, well, it's easy because it's all, dividable by 10, so.
Well, you guys have sat through a lot. You have more. Yeah.
I'm sorry.
Yeah.
I wonder if you could compare your process from your approach to the exterior insulation with the Kruse house, where they use, I think, 3 layers of rigid outside the sheathing. I mean,
Maybe like a foam, exterior foam versus the iDress?
right,
Yeah.
This would be the vapor barrier or vapor.
Well, so I guess I'm just thinking if you're using, even though I said I really believe that moisture in the walls comes from like rain and stuff like that, bad flashing details. It just seems to me like if you have, an open layer on the outside, something with a high perm rating, if you do get moisture in it, it can dry to the outside. I'm thinking if you have foam on the outside, it's not going to dry to the outside, so it's probably not really a big deal, but I just like the cellulose, it's like I'm a carpenter. I like to build stuff out of wood, and then afterwards fill it up with something else rather than like nailing foam on.
We've
I
done
think it's cheaper. I mean,
we've done some exterior foam houses, and the carpenters hate it. They really don't like doing it.
it's soft, you can't
It's
nail
soft
to
and
it.
squishy,
yeah.
I guess it's like the carpenter's like it's all wood.
Then you
It's
put wood,
stiff.
then you put like a piece of
Like a wood
strapping and
building.
screw through it. But if you screw too much, it ends up dimpling in. So
On the commercial side, I think it's all different,
Yeah.
but on the single family Maine carpenter thing, the iJoy stuff lines up so well.
that whole wall
Cutting
system
these out
just
of
seems
wood.
to me like everybody knows how to frame up the 2x6 wall. So all you got to do is throw these I-joists on the
Yeah.
outside. It seems pretty simple to me.
Yeah.
So
We hear a lot of guys when they do the foam houses, there's just foam blowing all over the yard, and they hate it.
oh yeah.
It's like scraps. And
I
stuff.
found it
Things
in-
like that bug people as much
You
as
find it
anything.
in the slab actually. I've found it in that
Yeah.
finished concrete slab. We were like, what the hell is that? All these small white specks, and it's all that small pieces from the cutting the foam to make that chamfer and thicken that slab. So, or ripping it, So
Yeah, it's funny. It's bits like that because we've done a bunch of exterior foam houses, and usually people don't want to do them again. The main single family home builders. The commercial side, they're used to it. It's really just another thing. But yeah.
yeah, I mean, I guess you can do it anyway, but
Because it seems to come down to labor. Materials probably aren't that much different. It really labor rates. But asking someone to do the iJoist wall the first time, if we've got a builder who we've never worked with before, and we ask them to do that, we've got to have all our powers of persuasion on because it looks weird. Hanging
but
iDress
it
outside
really
the-
is very simple. I mean,
I know,
there's
that's
nothing
like,
to it.
oh, it's so much easier.
So that's what, yeah, I mean, it's night and day. I thought the double stop wall was going to be really simple. It turned out to be a huge pain. And the TJI seemed like really challenging, and then you do it and you're like, huh, well, that was easy. It's like, okay, now what? So,
It seemed like you had, through elaborate strapping, to keep membrane from getting bulged out
yeah,
by the cellulose.
yeah.
Could you have a sheathing, like a zip panel, that would do both the WRV and eliminate the strapping? Does that make sense?
Yeah, I guess you could. It's
Just
just,
make it rigid so you wouldn't have this floppy barrier that you then have to do
Yeah,
strapping.
yeah, but the nice-
Take this zip and be done.
yeah, I guess you could. It's just the barrier is actually really nice because it's, it's a 5-foot roll. It's easy to roll it out. You can tack it up a couple of places, tape it. It's like, it's not like you're lifting up pieces of plywood. It's vapor open to the outside, and the strapping in that one photo, it probably looked like we spent like a couple of days nailing it on, but it goes really quick. I mean, it's like you shoot it on as you're putting the membrane out. You've got 5-foot pieces, you shoot them right on, crank your pump staging all the way up, so you got all your vertical pieces of strapping, and then you put a flying batten, because the TJI is a space 2 foot on center. You want to have a batten in between that, because that's where it's going to blow out against the siding, right? So as you start putting your first horizontal piece of strapping, we just take a piece, slide it up there, screw it through the horizontal piece into the flying batten that's in the middle, and then as we go down with our horizontal battens, as we go down, because we're putting on vertical siding in this case, then you put the flying batten in and you screw it in to that, and it probably takes, I don't know, maybe a day and a half, 2 days max, I think, to do the whole house. So, yeah, I can't tell you how much that membrane, I really like it, and it makes me feel really good when I'm standing and I'm looking at that membrane and the 2 inches of airspace between the membrane and the siding. I'm just thinking, all right, if water comes in here, I got 2 inches where the water has to travel horizontally before it comes into the membrane. That can withstand 38 feet of water, so I'm just feeling, man, nothing's going to get in there. Maybe I'm wrong, but it just feels really good. I mean, I feel confident about it. So, but I mean, like, you know, there is no prescription for how to build a passive house, so you could, you know, I think it's also like whatever your builder or, you know, whatever you're comfortable with, you should kind of go with something, you know, also maybe try not to spread yourself too thin and try too many new things all at once, you know?
Yeah, exactly.
Maybe kind of like introduce a couple of new things every time and then kind of, you know, work your way up to it.
Yeah, you can only handle, what, 3 new things on each job?
Yeah, I mean, you've got to sleep too. You can only lose so much sleep, so.
Especially with the architects who aren't in control of the job site anyway.
I have a question about alternative installations for that TJI cavity. Has anybody used like a mineral wool on the exterior? Or have you seen somebody try that?
Because we're about to, so we
There's no reason why it shouldn't work.
Yeah.
I mean, it should work.
I'm just thinking, you know, the cellulose is just easy to install, you know, because it's like somebody taking a big pipe and...
Could you call someone?
Right. I don't know, the mineral wool, are you using battens
I'm
or?
thinking about doing that instead.
Yeah, so I'm just thinking with the battens, you know, you have to cut them.
That's because you try to do everything by yourself.
Or are they...
How else are you going to do it?
I mean, that is part of it.
Yeah, I know. Like, you can't call anybody.
I mean, you could use anything, I think, you know, I think it's just a matter of you making... I mean, probably with a mineral wool, maybe you can get a little thinner
I'm just
wallet.
wondering if you've seen it done.
I haven't seen it done, but
It makes sense. I mean, it's just insulation. It's
there's
like,
no reason why you couldn't do it.
you know, all those things about bad insulation, like the voids and all that, goes away because it's on the outside of the house. And it can dry to the outside and there's nothing there, so go for it. Tell us.
Yeah, please.
Well, the problem that I'm thinking about is the bulging of the membrane, right?
Yeah.
The fiberboard, people like Hammer and Hand out in Oregon use that Autopon tongue and groove stuff to combat that. It's very expensive.
Right.
So you're expecting the fiberboard is actually helping the gear, but it doesn't. It's very difficult.
Yeah, that made it life pretty difficult and miserable, I thought. Plus it's like nasty to cut and stuff, so getting that membrane is just really easy, and then the strapping, you know, it's like, for that house you saw there, I think all the strapping was like $400. You know, it's just like rough cut 1x3. You just...
Are you using PT for that?
No, just use, I mean, I use down on the bottom, I use a piece of pressure treated 2x4 to block out my TJIs, but now the bottom part, I'm all right with just using the hemlock. So I use hemlock for that strap and just letting it it's a little more weather resistant. But.
All right.
All done?
Yeah.
All right.
2 hours.